So what happens here in the thermal simulation then? Let's take a quick look at the material properties. Here's our aluminum, and we have 0.045 for the emissivity, and our temperature is at around 1148 Celsius, so pretty hot. And if we take a look at the monitor results, so we do have a monitor again set up here on the outer surface. So 1D results, monitors on faces, outer. Here we can take a look at the convective heat flow, radiative heat flow, and overall heat flow. And we see we are radiating off quite a bit of heat, but a lot less than we're losing through convection. And yeah, so how does that change actually if I were to make no other change, but simply do switch the emissivity to a high value of 0.9, as it might be if we have a lacquered surface here. If I look at the temperature, I can see it's at 500 something. So we've basically halved the temperature simply by assigning a different emissivity on the surface. And if we take a look at the monitor results here, we can see the radiative heat flow, convective heat flow, and overall heat flow. We are now radiating a lot more. And I'm just mentioning it because the emissivity is something we always need to set, because in the material properties it's generally set to 0 from the get-go, and it's also something which is not really a bulk property, not really a material property in that sense, but a surface property which depends on how the surface has been treated. Okay, so we have good surface properties here now. We have a high emissivity. We have a much lower temperature, which is still really high. So what do? Let's think about adding some liquid cooling. Okay, so maybe I extend this here a bit. Let's see. So by something, add in a liquid cooling channel. Okay, let's assume this is done. Let's take a quick look here. And here we have this already set up in the model. So if I just take a look here, a base plate has been added. We have a liquid cooling channel here. And then what do I need to do? So I need to set some lids, which tell me what's going on there. So I have the lids for port 1, 2, and 3. These simply make sure that we have an adiabatic separation of the outside and the inside air. And I have lids cooling liquid entry and exit over here. And I can see here I'm telling it, okay, the boundary type is open, which just means it doesn't mean that we're actually open. We have a lid, it separates the outside and the inside. This is to be understood that we are simply making a shortcut here. Instead of extending this pipe to the boundary, we're starting it here. I'm coming in with a fixed temperature of 20 degrees Celsius with the cooling liquid volume flow rate, which is something like 1 cubic meter per hour. Okay. And on the other side, I have again an open boundary type. The temperature is set to ambient, gauge pressure 0. So the temperature doesn't really play a role here. What plays a role is that I have set a gauge pressure of 0, which simply means on this end, just see what happens. And yeah, so we can see temperature is now down to 133 degrees. So this is very nice. Yeah, we can also take a look at the velocity here. Let's give it a moment to load the results. And I'll just turn off the fields on plane. And I think I picked the face there. So let's look at some streamlines instead. And here we can nicely see the streamlines on the inside. So this is how the flow goes in there. And of course, it would be relatively simple to now play around with what's the temperature of the liquid going in there, what is the velocity of the liquid going in there, adding different pattern maybe in this cooling channel here. And with this, I can relatively easily make sure I get the results that I need. I can also, of course, again set monitors on the inside as well as the outside, and then compare how much heat am I losing to the outside, how much heat am I losing to the inside. So if I take a look here, we can see the inner convective heat flow, the outer convective heat flow, and the outer radiative heat flow. And if I take a look at the ratio, all of this, I can see that basically 97% of the heat go to the inside. So 97% of the heat are picked up by the liquid cooling that I have put here. So that's already a very nice result, I would say. All right, so I did set up the lids, but I didn't explain how I set up what kind of liquid is flowing in here. So let's take a quick look how that is done. Here I can see the fluid domains, and setting up fluid domains is really easy. So I just say, I would like to have a fluid domain, and then I pick some face on the inside. So I'm not going to do that because I don't want to lose the results here, but you can see I picked this face in here, and then the solver knows, here is the cavity from the mesh. This face was picked. I am I am terminated by the lids that have been set here, and it will automatically assign this fluid domain where I picked the material of glycol water that we can see here and use this for the simulation. And the glycol water is actually set up here as a temperature-dependent material with a temperature-dependent dynamic viscosity, heat capacity, and thermal conductivity. All right. So I already have a relatively good overview what happens here, what happens with no surface treatment, if it's polished metal, what happens if I have a surface treatment, what happens if I put in liquid cooling. What else might I like to consider maybe? Well, I could think about, okay, I have looked at the filters so far, but I haven't really looked at, well, what influence do the waveguides have that will be attached here? And what would the temperature of a waveguide on its own be? Something like that can be relatively easily looked at. So we just take a quasi 2D slice of waveguide here, run another F-solver simulation, then import losses, run another CHT solver simulation. Actually, this one here with the quasi 2D setup is a little bit tricky, but will be much easier in 2025 with regard to the boundaries. And yeah, so here I get a good idea for what the temperatures on the waveguide is. If the waveguide was to be undisturbed, so I'm going up to around 150 degrees Celsius, which is actually a little bit hotter than what we had here for the temperature, which went up to, I think it was 130 something. And yeah, so now I could also consider, how does this influence, how does it influence results if I now start adding waveguides, and how long do I have to make these waveguides before before they don't influence my filter that much anymore? And